Logarithmic differentiation is a very powerful tool that enables us to take derivatives much more simply. Suppose I have a function like this. Now I can take the derivative of this using the product and quotient rules, but I don't necessarily want to. I want to take derivatives of simpler functions. And one way to do this is what we're going to call logarithmic differentiation. Now, the crux behind logarithmic differentiation is I'm just going to take the natural log of this whole thing. Okay, I'll do it this way. And then I'm going to do implicit differentiation and solve. Let me give you the steps I want you to follow. I want you to take the natural log of both sides. And then I want you to use logarithmic properties to separate them. Take the derivative of both sides, simplify, and solve for y prime. Now the biggest trick here is you have to remember that when I take the derivative with respect to x of the log of y, this is going to be 1 over y times y prime. And you'll see me write y prime over y. So suppose I have this function here. Y is x minus 2 squared divided by the square root of x squared plus 1, such that x is not negative 2. And clearly y can't be 0 here for my log function. So the step 1, I'm going to take the natural log of both sides. X minus 2 squared divided by the square root of x squared plus 1. Now this is my equation editor. This is not part of the equation. Now I'm going to apply the log rules to simplify this out. So this is twice the log of x minus 2 minus 1/2 the log of x squared plus 1. Now I'm going to implicitly differentiate this whole thing. So this side becomes y prime over y is equal to, now look at this side over here. Look how beautiful this is. The derivative here is 2 over x minus 2 minus 1/2 times 2x divided by x squared plus 1. So I can rewrite this side 2 over x minus 2 minus x over x squared plus 1. Now the beauty of logarithmic differentiation is, in general, I don't make you do a whole lot of combining terms. But I'm not done because I'm looking for y prime, which means I have to go back and substitute back in what y is. So I'm just going to multiply by y here. But now I need to go back up and let's see, what was y? Y is, so I need to plug what y was back into my equation. X minus 2 squared divided by the square root of x squared plus 1. I'm out of room. This is a big square root times 2 divided by x minus 2 minus x divided by x squared plus 1. Now the derivatives were much easier using logarithmic differentiation than the product and quotient rules. We can also find relative extrema. Relative extrema will be where the first derivative is 0. So I find y prime, and this is this whole denominator. And now I need the derivative of the numerator, and that's 2x plus 2. All right. I didn't really need logarithmic differentiation for this one, but this is a cool problem. So y prime is 0 when 2x plus 2 equals 0, or x equals negative 1. So the extrema, y at negative 1, is the natural log of negative 1 squared minus 2 plus 3. So this is the natural log of 1 plus 3 is 4 minus 2. All right, so I have an extrema at negative 1 log of 2. Now, is this a max or a min? Well, let's look. We can do a number of things here. We could do the second derivative test or the first derivative test. If we use the first derivative test and we look at y prime, we see that this goes from negative to positive, so this is a minimum.